So yeah, I'm so happy to be here. I worked at AI Redefined, and we enable enterprises to design, build, and operate AIs that team up with humans. And today I want to share with you what we've learned building products that leverage both artificial and humans intelligence, especially in high-stakes use cases. I want to show you what's possible to do, what are the challenges, and how to address those challenges. More importantly, I want to shift your perspective from thinking about AI as like a monolithical end-to-end system to think in terms of intelligence ecosystem that mix human and artificial intelligence. So yeah, AI is big, AI is changing the world, it's the new revolution, whatever. What's important is that this revolution shouldn't continue without taking into account the human factor. And I don't want to talk about machine uprising, at least not for now, but about actual concrete problems that the current generation of AI has. First one is context and alignment. AI's actions don't align usually with human intent because they are not aware of context. When I talk about context, I want to mention that AI are narrow-minded. They don't understand why they are making decisions. They don't understand the impact of those decisions. And on the flip side, humans are usually good at that. They are good at understanding the bigger picture, to take a step back, etc. And that's one of the causes of this alignment problem. The new generation of AIs need to be able to take into account, to leverage those human skills and to let them supervise the AI decision or learn from those humans' decisions. Second problem is that actually AIs don't really learn from collaborating with humans. AIs don't really know how to collaborate, to adapt to their human coworkers. For sure, we've been training AIs from annotated data for years. I mean, reCAPTCHA is exactly that. We've been training robots by proving we are not robots since 2007, something like that. But in practice, it's not collaboration. The humans is actually playing the robot game to be able to train the robot. And even in deployed system, you can think about fulfillment center, for example. We are deploying workflows that are suited to AI systems and then fitting humans inside those robotics workflow. And that's pretty much concerning in a world where AIs gets applied to a bunch of use cases and to more and more use cases. So that's what we believe needs to be addressed. The deployment of AI needs to be truly beneficial to humankind, so we need to be able to address the challenges to do that. But furthermore, we need to address the challenges to create better AI that are able to learn from their human friends. We call that long-term objective human-AI synergy, and AI Redefined at its core mission is trying to create the condition for this human synergy. And we are doing that by creating what I will be calling intelligence ecosystem in this talk that continuously learn from their experience of shared experience of human-AI collaboration. The good news is that the techniques to do that already exist. They've been developed in academia for a while now. And I want to show you a few examples of those techniques and see how they can be transposed to real-world use cases. OK, so the first category of techniques I want to talk about is what is called behavior cloning or imitation learning. And the idea is pretty simple. You have humans performing a task, and the AI is learning how to perform the task by reproducing, by cloning the behavior of the humans. A first early example of this kind of techniques is Alvin, which is an early autonomous driving system developed in 1988 at Stanford University. And it showed interesting results. Of course, it's not there yet. Otherwise, we would have autonomous cars everywhere. But it shows interesting results in this kind of sequential decision-making that are required to do driving. And that's very different than perception tasks like the one that we are training AI for with something like reCAPTCHA. One challenge of those kind of behavior cloning systems is that you need a lot of data to be able to account for the dimensionality of those sequential decision-making, because basically, if you don't have enough data, the AI can get lost whenever it strays away from the path that's been pre-recorded before. You can manage this kind of issues by having an interactive system where the AI can say, hey, I'm lost, can you help me? And the human expert can then provide additional information, additional demonstration. But this causes additional technical challenge. So yeah, behavior cloning works. You can have fast initial training, and you can have this continuous interactive refinement afterwards. You are quite ensured of the alignment because basically the AI is just reproducing what it saw the human do. You don't require specific additional human skills. The human just need to be able to do the job. But you have bounded performances. The AI will only be able to do the job as well as its human demonstrator. And even when you need a lot of data, it will average out and be just okay. So to address these kind of problems, we can look at reinforcement learning, especially reinforcement learning with human feedback. And I want to mention works done here at the University of Texas called Tamer in 2009. And so the idea is that it's much simpler for someone to evaluate how a task was fulfilled than to fulfill the task themselves. So let's use this information. I want to do a quick aside on reinforcement learning because those methods use reinforcement learning formalism, and it's not something that's as well known as supervised learning. So supervised learning, we all know what it is. It's basically providing examples of how to do a task and let the human learn from those examples. Reinforcement learning is objective-driven. You tell a task what's the objective using some kind of function, and the AI will learn by trial and error to find a good way to fulfill this objective. That's how DeepMind researchers were able to beat a lot of the Atari games a few years ago, the reward function being the score of the Atari game. So this trial and error causes different kind of challenges. The first one is that you need a safe environment to do that. You can't do trial and error in the real world most of the time because you might end up in dangerous situations. And you need to have those safe environments, which are basically simulations that are quite fast because usually you need to accumulate years and years of experience for an AI to be able to do something useful. The second set of challenges is this reward function. Usually, in real-world tasks, the reward is not as easy as using the score from an Atari game. So to address those challenges, we can use humans. So let's go back to Tamer and its successors. So on the right-hand side, you can see a method called Deep Tamer that was used to basically create agents that are better than at Atari games than the one trained without human input. You can see here the blue curve, which is the agent learning. You can see that in 10 minutes, it gets better than the average level of its evaluator at the game. So they managed to train an AI that's better than them. And in 15 minutes, the AI gets better than the best human at this game. And you can see also that on the bottom, you have the regular reinforcement learning method. And Deep Tamer is learning much faster. It's learning much faster because it can learn from the expertise of the humans in this game. The other example is Coach. Coach is the same kind of algorithm, but in the real world. And they are training robots to do fetch tasks in a few minutes by giving them feedback. So yeah, this approach enables superhuman or even optimal performances. You still have control over the alignment. The human can provide really rich information in the reward and can basically reward an agent that's doing what the human intend the AI to do. It requires some specialized skill. You need to understand how the AI learns to be able to give good rewards. And one thing that's little touchy to do technically is that when you have a reward function, the reward arrives instantaneously during the training process. When you have a human acting as a reward function, the reward can be delayed. And you need the full system to take that into account to be able to train properly. And last but not least, it requires a safe environment, which is basically usually a simulation. Building upon those two kind of seminal work, see something that we've done at AI Redefine. That's a little mix of both. That is akin to dual control at driving school when you have like a monitor that is able to take over from the student. And the idea here is to use human demonstration, but not to use them as reference, but to use them as a way to explore the world in an easier way. So that's a typical reinforcement learning benchmark here, where you are trying to land a spaceship between the two poles. And whenever there is a red outline, it's because the human is taking over from the AI. So interactively, it trains the AI to perform the task. But the AI is not using those demonstrations as a reference. It's using those demonstrations as a way to provide further information about what actions leads to what. In terms of results, it's interesting. So the blue line is the traditional reinforcement learning method. After a while, they cross this horizontal threshold, which means that they manage to learn consistently and then gets better, which means they learn faster and faster. In our case, we have a first part, which is the red line, which is the performances of the team, the AI plus human team at the task. So basically, right away, it manages to learn consistently. And it would be even better if the demonstrator, which is me in this case, would be better at the task. What's interesting, if you transpose that to a real-world scenario, is that what it means is that the team can be deployed right away. The team can be fulfilling the task. Of course, the human will do most of the work, but then gradually the AI will be able to take over, and that's the orange part of the curve. Even when the human stops interacting with the AI is consistently better at the task than an AI that didn't benefit from this human expertise. That's an approach that we call AI apprenticeship, where basically you have a mentor and an AI student that learns on the job. What's interesting about this approach is that the training goes both ways. The AI is learning from the human expertise, but the human is also learning to trust the AI to understand how the AI is performing the task, where it is good, it is bad. So yeah, with this kind of method, still you get superhuman or even optimal performances. You have still control about the alignment of the behavior of the AI. You don't really require additional human skills. The human just perform their job. But there is an emphasis to have on the UX part, where you need an interface, an interactive setup, where operationally the human can perform his job while training the AI. And you need to do that during a training phase, but also during operations to benefit from this AI apprentice approach. Before switching gear to actual industrial use case, I want to mention this work. So this is work by OpenAI that was done in 2020 and 2021 on summarization, so basically taking a text and generating a summary. The approach they have taken is let's pre-train a language model, a GPT-style large language model over the internet, and then use human interaction to fine-tune this model to create better summaries. So they are using humans both as demonstrators that provide reference summaries and also as evaluators that give preference between variation of summaries. So you can see the result on the right side. The orange curve is their human feedback method that shows that the generated summaries are preferred by human panel. Interesting learning from this work. The first big interesting learning is this ability to fine-tune something that has been learned traditionally. Learning with a human in the loop is costly because you need to have the human in the loop. So it's important to do the most of the work without the human and then target where you use the human manpower. They show that it works even on large models. They are using hybrid technique. It's not just about using demonstration or feedback, it's using both. And contrary to the other tasks that were more toy examples, this is on a language task that's something much closer to what the industry is actually using. And the last but not least, this method is about improving alignment. So they've shown that by using human, they're able to provide summaries that are more aligned to the human expectation than previously. Okay. So the first real-world example I want to share with you is a domain that's called man-machine teaming in the aerospace and defense industry. And man-machine teaming in this industry is seen as kind of an objective. They realize that they will need to create machines and AIs that fulfill complex tasks, but they also need to keep humans in the loop because of the high stakes of the decision that they are making. They need the accountability and they need the sensibility of the human. So they are developing techniques for this teaming to work and to be efficient. This is an early example of the work that we are doing with a company called Thales, who is a leader in the aerospace and defense industry. And their goal is to create a platform to train and operate fleets of drones that can collaborate with human pilots. And so in this example, you have autonomous drones that are scouting terrain, a forest for fires. And you have a human pilot in a helicopter that's there to go from fire to fire and extinguish those fires. So the two needs to collaborate to efficiently extinguish the fires. The way this was implemented in this experimental platform is as a training application for human pilots. So the idea is to train helicopter pilots to better collaborate with the drones. They can they learn how to use the information provided by the drones, and they also learn how to give orders to the drone when they want to have specific information about a part of the terrain. And in fact, all those signals that are provided by the humans are used implicitly to train the drones themselves. So in practice, it's a platform that's training the team of human and AI drones. And having implicit signals means that we remove part of the bias in the training process because the humans are just performing their job. They are not trying to make the AI do something. That's the first benefit of this kind of approach. The second one is you are not wasting time. Basically, you are training the humans alongside the AI. It's not dedicated time of the humans to do something. They need to train. For sure, for that kind of thing to work, you can't start AIs that are just completely dumb, randomly exploring reinforcement learning agent. You need to have pre-trained those AI. You have basically two ways of doing that. Either you start with reactive doctrinal behavior, so heuristics-based behavior for those AI, and you train on the side new version of the drones, and then when they are ready, you deploy everything. Or you can pre-train in the same setup by replacing the human with an AI system that will train those drones to get the basics. And last but not least, this kind of system enables real-time human supervision and enables the agent to train to understand this human supervision. So here, the human can give orders to the drone. We have worked since then in examples where the drones have some actions that requires pre-authorization from the human to be able to be performed. And those kind of setups means that the drones not only need to know which action that they would ask the human for, but also to teach the drone to anticipate the time it will take for the human to accept or refuse an action. So in the previous example, we already had some kind of heterogeneous collaboration because the drones and the helicopter had different ways to interact with the environment. And to go beyond that, we've developed this concept of intelligence ecosystem. In this example, it's really pushed a little more. So this is something that we've developed with the city of Hong Kong, and more importantly, with the emergency dispatcher of the city of Hong Kong. So basically the people who answer 911 calls and then decide to dispatch an ambulance or a tow truck or a firefighter vehicle to an emergency. And so those guys, they can be overwhelmed by the number of emergencies they have to deal with. And so they would like to have AI assistants to help them even the workload, to help them even their cognitive load. But on the flip side, they are making really high-stakes decisions. And so they need the humans to be kept in the loop of those decisions and to provide accountability for those decisions. So the way that we've been approaching this collaboration is by developing a dynamic assistance AI that gets out of the way when everything is fine and that have more autonomy and helps on some of the tasks that the humans are doing when it's in crisis mode. So you can see here the prototype UI that was developed. Basically, the human received emergency. Each emergency is get a recommendation dispatch from an AI system that the human can edit, fully accept or partially accept or completely reject, and then dispatch. And the AI can also make fully autonomous decisions that the AI can then, after the fact, review. Under the hood, it works like a multi-agent system. We have, in fact, different kinds of agents. The one that deal with the routing of the unit, the one that deal with the dispatch of the unit, the evaluation of the priority of those emergency, the evaluation of the autonomy level that can be taken by the AI, so whether or not it should take fully autonomous action or just do recommendation, and the role taken by the human here, which is basically accepting or rejecting recommendation. And in terms of project, we started by developing a very first simple version of those agents with basic heuristics, which meant that we were able to deploy something really quickly. And because it was deployed very quickly, we were able to first get insight about how the system was used by the operators, but also get data and start training agents on those different roles while having a baseline of the performances. And in the end, we actually replaced, at this stage, we only replaced 2 of the agents. The first one, which is the dispatch one, was replaced with a constraint solver, so nothing to do with machine learning. And the second one, which is the autonomy level, deciding whether or not to take a fully autonomous action, was replaced with a reinforcement learning-based agent. But this kind of modular approach paid dividends because of this kind of gradual deployment and the ability to generate data from day one, basically. So yeah, faster deployment and faster iteration. This ability to have several roles, some of them that can be taken by humans, some of them that can be fully autonomous, enables different degrees of supervision based on the needs that you have. And the fact that you have smaller footprints agent means that you can more easily do compliance check, decide to do some part that are fully explainable agent, etc. And so beyond those obvious use cases where humans' lives are at stake, there is a bunch of other verticals where humans actually are doing most of the job today and would benefit from AI that can collaborate with them. So I've listed a few here. We are currently working a lot in utilities and education, but transportation, especially autonomous driving at higher level of autonomy, is something that makes sense, and else for sure makes sense. So let's kind of recap the benefits that I've talked about. The first one is this ability to leverage human expertise. It's important to be able to train better AI that are able to understand more things in the context, that are able to train quickly because of the usage of human expertise. But it's also leverage this human expertise at operation time and be able to mix between a fully supervised system and fully autonomous system, and foster collaboration. Second benefit is this ability to deploy faster and continuously. The idea of having smaller footprint agent that you can develop first version of quite easily makes it easy to deploy something quickly. The idea of AI apprenticeship makes it easy to have something that will grow gradually and be more and more autonomous. And last but not least, this idea of trust. When you are putting in the hand of the same humans that will have them as coworker AI system from their inception, you are building this trust relationship. You are building the humans are building a mental model of how the AI systems react, behave, and because of that, they're able to trust them more. Of course, it means a bunch of challenges, technical challenges. The first one is continuous learning, and it's really important to have that in mind. You can't have this kind of gradually deploying system if you have a traditional pipeline which will be train, validate, deploy. You need to have a continuous update of the training model. You need to have online learning. You need to mix and match multiple AI techniques, not only machine learning technique, but also plain old AI. And you need to be pragmatic about that to be able to capture the most of those human signals that you can. And last but not least, you need to be tech agnostic. We are talking about having a tight integration between AI systems, between simulations, if you want to do this kind of pre-training, between data pipeline of data ingress and also egress to real-world system, between UX systems. So you need to orchestrate between all of those in real time to provide online learning things. And it's not only different texts, it's also different culture and different engineering approaches. So yeah, of course, that's why we built Cogment. So Cogment is our open source platform. It's there to build, train, and operate AI agents in those kind of shared environment. And it's designed to help those different engineering culture to collaborate with each other and those different tech stacks to collaborate with each other. It's enabled this ability to continue to train AI and humans together to operate those intelligence ecosystem. And it's designed to move from a simulated world, a fully simulated world, to a fully real world with the same setup and with the same orchestration platform. It's available as an open source platform. We are already being used by a bunch of research labs at this stage, and we are providing, as a company, commercial offering on top of the open source platform in the areas I was mentioning before. So yeah, what I want you to take away from this talk. The first thing is that when you are designing AI-enabled products, in fact, you are not designing AI-enabled products. You are designing human-AI relationship, and it's a UX problem, for sure. It's a design problem, but it's also an AI problem, and it's also important to consider the different kind of AI techniques that you can leverage to facilitate this collaboration. The AI apprentice approach is something that really we believe in, and that will facilitate the deployment, the early deployment of these kind of techniques. Most of those AI training techniques are quite advanced. Some of them are not really ready for prime time. So having something that can be gradually learning, that can have different level of supervision, helps with testing right now those techniques. And last but not least, this idea of thinking in terms of intelligence ecosystem, in terms of distributed decision making that involves both artificial intelligence and human intelligence, will make you design simpler and more effective systems that can benefit from future and better techniques. Thank you. That's us. We are hiring. We are in Montreal. It's very cool. And I will take questions now.